Welcome back to Calculus 1. This is part 2 of our lecture on the limit of a function, picking up exactly where part 1 ended, discussing the relationship between one-sided and two-sided limits. In this part, we're going to jump straight to another example. All right, now previously we saw the relationship between one-sided and two-sided limits, which is basically where part 1 left it off. If the individual one-sided limits are different, that then means the two-sided limit does not exist. So we're going to follow up on that here with example 3. This example gives you the graph of a function, and then it asks you to use the given graph to evaluate some limits. All right, this function's a little weird. Notice there's kind of a gap, there's a hole, but this is a standard type of function that the language of calculus is able to deal with. So right now we're thinking of limits. So pause the video, give yourself an attempt here. This example in question is asking you to use the graphical approach to limits. We'll check in a few minutes. All right, welcome back. Let's go through each part individually. We'll start with part A. All right, and what this is for part A is a two-sided limit or limit. We're letting x approach 5 from both sides simultaneously. So we visualize on the x-axis values of x closing in on 5 from both directions, and we imagine each of those x values has a corresponding point above it on the graph. So we follow along the graph, and as we get closer to the point with x coordinate 5, it looks like the function or y values are getting close to that point on the graph, 5, 1. So since the function values are getting close to y value 1, we say this function has a limit of 1 as x approaches 5. All right, let's take a look at part B. Part B is also a limit or two-sided limit. And now something weird's happening. Notice the hole in the graph. There is no point there. The function value was removed from y value 2 up to y value 3. This type of graphical feature is something that we'll define in a following lecture as a removable discontinuity. But right now, it's a graph. Notice it passes the vertical line test. If we throw in some review there, what we couldn't have, which would fail the vertical line test, is two closed points or function values above one another. That would then fail the vertical line test. Graphically, we can have as many holes, open points or circles on a graph above one another, since there's no function value there. That would all pass the vertical line test in that case. All right, so here, as we let our x values approach 1 from both sides, notice as we follow along the graph, we get very close to that hole, which is at y coordinate 2. So as we let x approach 1 from both sides, the function value or y value approaches 2, which is the limit. All right, but I want you to notice before we move on, the function value, f of 1, is actually defined to be 3. That's where the filled in point or function value is at 3 for the y value. So here, the function value is 3, but the limit value is 2. That's something we'll elaborate on in a following lecture. Let's move on to part C. Part C is now a one-sided limit. We're approaching 3 from the right. And as we, again, kind of imagine plugging in, moving through values of x bigger than 3, that's approaching 3 from the right, we follow along the graph, and it looks like, again, the function values here approach 2. So graphically, we would say the limit here is 2 as x approaches 3 from the right. Okay, part D is now a one-sided limit, but now from the left, the other side. And this function has a gap. That'll be something we define as what's called a jump discontinuity. From your pre-calculus course, you might be comfortable with these when you were asked to graph piecewise defined functions. But here, as we approach 3 from the left, we just follow along the other upper part of the graph. And as we do so, the y or function values get close to 3. So the limit here to 3 from the left is 3. All right, now recall part 1 left off stating the relationship between one-sided limits and two-sided limits. Take a look at part C and D. We're approaching 3 from different directions, and the limits, the individual one-sided limits, are different, 2 versus 3. What we can then conclude for part E, and part E, notice notationally, is a limit, a two-sided limit. Well, as we let x approach 3, that limit does not exist, since the individual one-sided limits are different. They're not equal. All right, so that concludes example 3. That was following up where part 1 left off. Let's get to kind of the next topic within this lecture. This one is kind of an introductory lecture, getting all the ideas for limits out of the way, kind of from a very basic point of view. So the next idea we're going to look at is that of what's called an infinite limit. All right, now, again, if you think back to your pre-calculus course, there is a concept introduced in your pre-calc course that kind of motivates what we're going to call and define in calculus as an infinite limit. So here I'm kind of telling you what that idea is. You might not remember the name, but the graph of y equals 1 over x, that type of function is called a rational function. And you might recall in your pre-calc course, for rational functions, finding the equations of their horizontal and vertical asymptotes. All right, so here's the simplest rational function, 1 over x, which has a vertical asymptote, x equals 0. You can see that algebraically, since this function becomes undefined at x equals 0. And there's a horizontal asymptote of y equals 0. This is kind of like end behavior. As you go very far to the right or left, those are the big values of x. Then you get 1 over a big number, which becomes small, approaching 0. All right, so we'd say that's the reason why this function has a horizontal asymptote of y equals 0. As you go very far to the right or left, the function approaches the line y equals 0. Okay, now we're using this, again, graph to motivate some calculus concepts, that of an infinite limit. And what I want you to notice is we're going to take a look at a limit as x approaches 0 from both sides. This function is undefined at 0. Notice if you plug in x is 0, you get 1 over 0, which is undefined. But recall with a limit, as we're approaching 0, we aren't actually concerned about reaching x equals 0. We can get as close as we want, but we don't care about reaching x equals 0. All right, so graphically, if you are comfortable with this graph, you can see as you approach 0 from the right, the graph goes up towards positive infinity. And as you approach 0 from the left, the graph goes down towards negative infinity. Now, over on the side there to the right, there's 2 useful ideas that we're going to use frequently throughout our course, which basically capture what's going on with the function and the limit here. So the first one, not boxed, is a starting place. Think of if you have 1 divided by a really big number. Think 1 divided by 1,000,000. That actually comes out to be a very small decimal value. So 1 divided by a big number is small. Right above that, in a box, because stuff in boxes means it's clearly important, we have the inverse relationship that we're going to use now. Flip that around, 1 divided by a small number. Think 1 divided by 0.001. That actually comes out to be really big. And that's what's going on with the function values here. As you let x approach 0 from either side, on either side of 0, close to it, are small values for x. either small positive numbers or small negative value numbers. All right, so as we approach 0 from the right, x is a very small number. 1 over x, 1 over a very small number, is very big. So that's confirming here why the function values shoot up towards infinity or down towards negative infinity. All right, now, before we advance and get to the definition of infinite limits, think back to when we defined limits in part 1. We said a function has a limit if all function values approach a real number. Well, notice what the function 1 over x is approaching here, infinity or negative infinity. Infinity is not a real number. It's not a number. It's a useful mathematical concept. So here, since the function is approaching something that's not a real number, technically, we say these limits for 1 over x, as x approaches 0 from the right or left, those limits do not exist. All right, now we're going to make a connection to your pre-calc idea to now calculus ideas with infinite limits here. Even though these limits do not exist, they tell you something graphically. Notice what's happening at x equals 0. This function has a vertical asymptote. So we're kind of alluding to a connection between infinite limits and vertical asymptotes. We'll make that more precise momentarily. All right, so realize before we get to the next point, these two limits down at the bottom there, as x approaches 0 from the right or left of the function 1 over x, both of them do not exist. Since infinity and negative infinity, what the function is approaching is not a real number. All right, now those statements actually tell you something about the graph and its behavior. So we're going to write the following. We're going to write that the limit as x approaches 0 from the right of 1 over x equals infinity or positive infinity. Why? The limit here technically does not exist, but that limit statement concisely kind of tells you what's going on with the graph of the function there. As you approach 0 from the right, the graph shoots up towards positive infinity, describing the vertical asymptote and the behavior of that function. All right, so that's going to be standard notation. We're going to realize those limits technically do not exist, but we write they equal infinity or negative infinity, since that's graphically telling us something. All right, let's get here to the definition of infinite limits. And it's really not that bad. The first part says if the values of a function increase without bound, and what we mean by that, if something increases without bound, it keeps getting bigger and bigger and bigger, and there's no upper bound for it. Something that's increasing without bound, there's no bound for it. Your function values will then surpass every proposed upper bound. All right, so if the values of the function keep increasing as x approaches a, then we're going to say and write here that the limit as x approaches a of f of x equals infinity, sometimes written as positive infinity for emphasis. All right, similarly for part 2 here, if the values of the function decrease without bound, if they keep getting smaller and smaller as x approaches a, then we say and write the limit as x approaches a for the function equals negative infinity. Okay, so this is defining infinite limits. Here we wrote it for a two-sided limit as x approaches a, but this would apply as x approaches a from the right and perhaps as x approaches a from the left. I didn't want to make it kind of a multi-part definition. Just swap out x approaches a for x approaches a from the right or x approaches a from the left. It's all the same. All right. Now let's make the connection between pre-calculus and calculus. Now, we can interpret infinite limits in calculus now graphically as the familiar concept from pre-calculus of a vertical asymptote. So if we have a function here, we'll be boring and call it f of x. So if that's our function, and if any of these three different limits equals positive or negative infinity, either the limit as x approaches a, that's two-sided, the limit as x approaches a from the right, or the limit as x approaches a from the left of that function, if any of those limits are positive or negative infinity, if the function increases or decreases without bound, then graphically, the vertical line, x equals a, recall that's the equation of a vertical line, x equals a number, then that line, x equals a, is a vertical asymptote. All right, now I realize what you might be thinking. Well, I kind of learned about vertical asymptotes before. Why do I need this new definition? Well, kind of ideas that you introduced in your pre-calculus course were kind of at a basic level. Now, once we reach calculus 1, we can use now usually limits to make some of those ideas more precise. So as you continue into higher level mathematics, precise definitions of mathematical quantities make all the difference. So that's kind of where calculus 1 is heading. Not all of you are going that route, but some of you might be. Okay, so let's take a look at an example. It's going to be dealing with one-sided limits. I'll just tell you in advance the next example, example 4, does involve infinite limits. All right, let's take a look here at example 4. We have the function 4x divided by x minus 1, and the question just asking us to evaluate the limit as x approaches 1 from the right and the limit as x approaches 1 from the left. All right, now if you feel like you're getting this, maybe pause the video to make an attempt at this. Otherwise, we'll just continue in a few seconds if you don't feel yet comfortable trying an example on your own. Typically in class, I give my students examples to try. In a recorded lecture, you can pause the video and make an attempt if you want. We'll check in a few seconds. All right, so I realize this might be a little new. One thing we're hinting at in part 1 is sometimes plugging in works. Well, let's try plugging in x equals 1. And if we do, plug that into the function f of x equals 4x divided by x minus 1. Notice your denominator becomes 0 when x equals 1. So plugging in x equals 1 here gives an undefined function value. So plugging in here isn't going to be useful. But what if I told you this is useful? What's going on here is as you let values of x approach 1, your denominator becomes very small. Recall a few minutes ago, we gave the useful idea 1 divided by a small number is really big. So we're going to make the following connection. We're not describing equality here. We're not saying division by 0 equals infinity, but kind of does. Well, we're going to say that when you have a number divided by 0, the result of plugging in with standard limits in calculus 1, that usually points to the limit either being infinity or negative infinity. Here, as x approaches 1 from the right or left. So again, just to state this, whenever you plug in and you see pure division by 0, a non-zero number divided by 0, that usually indicates that your limit is either positive infinity or negative infinity. Usually, but not always, for most simple calculus problems, that's usually the case. Okay, so the point of that was now we see by plugging in, we get 4 over 0. We might suspect we have one of 2 possible answers, infinity or negative infinity. Now that's actually a good random guess to take there. Any game where you have a 50% probability of being right, you want to play that game, like at like a casino. All right, so here you could just flip a coin and you either get a right or wrong answer. Well, the question we're going to deal with is how do I determine if the limit is positive or negative infinity? We're going to have a conclusive way to do that. Now let's go through this first part together, since this might be a conceptual jump from your pre-calc course to Calc 1. For most students, that's the biggest jump within the mathematics sequence. Recall, with a limit, we can plug in values for x that get close to a, but we actually don't care about reaching x equals a. We just plug in and get closer to the limit value that we're approaching, or the limit point. All right, so what we're able to do here is plug in a value that's really close to a. Here, a is 1. And that might be enough for us to make the conclusion about our limit being either positive or negative infinity. All right, so let's do that. Let's visualize on a number line what's going on. We're letting x approach a here from the right. We're going to look at the first part together. All right, and approaching 1 from the right, those are values for x that are a little bigger than 1. So we could pick any value that's bigger than 1, but we want to be close. I don't have a good answer for how close is close enough, but here I think most of us would say 1.01 is close to 1, but on the right. And what we're going to do is plug in x equals 1.01. Now we're going to try to do this without a calculator. What we're trying to determine right now is if our limit is positive or negative infinity. We're just basically trying to determine the sign. Now you could get the exact value here, plugging in 1.01 to that function, 4x divided by x minus 1. But we don't need that. So we can do this very quickly without a calculator. We're just going to plug in x as 1.01 to our function 4x divided by x minus 1. Notice your numerator is going to be a positive number, 4 times 1.01. That's a positive times a positive, which is positive. And then notice in your denominator, you have a number minus something smaller. That's always going to be positive. 1.01 minus 1 is positive. So what we have here is a positive over a positive, which cancels to a positive. So what that is pointing towards is that this limit seems to be approaching positive infinity, which is correct. So here for this function, as x approaches 1 from the right, we're approaching positive infinity since a value for x very close to 1 from the right was positive. All right, now with that out of the way, if you understand that, now you can probably kind of reproduce that to make an attempt at the other part, the limit as x approaches 1 from the left. We'll check in about a minute. All right, let's go through this. Now again, we're suspecting that our limit is going to be positive or negative infinity. So we're going to try to determine which sign for the infinity we want, positive or negative. And when we're doing a limit to the left here of 1, we're going to want to use a value for x that is less than 1, just to the left. So let's go with, let's say, x equals 0.99. That seems to be sufficiently close to 1 on the left. We're going to do the same thing. We're not going to try to calculate the precise function or y value, just merely the sign, which we can do very quickly. The numerator is a positive times a positive, so the numerator is positive. And notice now your denominator, you have a number minus something bigger. That's always negative. So your function value here gives you a fraction, a positive divided by a negative, which is negative. And that hints, it actually turns out to be correct, that this function, as x approaches 1 from the left, equals negative infinity. All right, so again, the clue here was plugging in. So at the beginning, we plugged in x equals 1, and we got division by 0. Division by 0 usually suggests that your limit is either positive or negative infinity. We use this work about plugging in a value just to the right or left to determine if we want positive or negative infinity for each limit. All right, let's get to one last example. This is the example that we were kind of alluding to at the beginning of this lecture, this part, when we were given the graph of a function and asked to determine some limits. Now we're going to flip that. This will be one of our first times that will eventually lead us to our long-term goal of curve sketching, where we're going to take some given conditions and then use those to sketch a possible graph. So here, given limits now, we're going to use those limit statements to sketch a graph. All right, this does get to be a little tricky, but it still involves the graphical approach to limits. If you feel like you understand everything, pause the video and give this an attempt. It's probably the most challenging conceptual example so far. We'll check in about 2 minutes or so. All right, now the long-term goal for us of curve sketching tends to be a little overwhelming for students. There's a lot of ideas leading into that, but we're not there yet. But this is our kind of first example that puts us on that path. Now I want to give you a tip, which is to try sketching just a small part of the graph near each important x value. So if you take a look at those 3 conditions, there's some x values referenced. In condition 1, within the function value, function notation, we have the x values -1 and 1. In the second and third conditions that were given, notice the limit notation, x is approaching -1, and then in condition 3, x is approaching +1. So our important x values here seem to be -1 and +1. Those are the important x values within this graph. All right, so let's start with condition 1. Condition 1 is just simply points on the graph, since we interpret function values as being y values. So from part 1, we have the ordered pairs -1, 1, and 1, 3, giving us these 2 points on the graph, -1, 1, and then 1, 3. All right, condition 2 is telling us something about a limit towards -1 from the right and left. So let's take a look at -1, and we're just going to draw a small portion of the graph. Now, as we approach -1 from the right, we're getting close to the y value up there, 1. So I have a small part of the graph getting close from the right towards y coordinate 1. All right, and when we approach -1 from the left, here the limit is 0, which is now below. All right, now notice here, since we were already given 1 point, -1, 1, I can't include down there on the x-axis at that point, -1, 0. I can't fill that point in. It has to be an open or hole, open point or hole. All right, if it were filled in, it would fail the vertical line test. Every graph that we sketch for one of these problems has to be that of a function. It has to pass the vertical line test. All right, so that's a small portion of the graph near -1. Notice it's very small, very close to -1 on both sides. And then condition 3 is a two-sided limit. And again, I drew a very small portion of the graph around x equals 1. Now, we were already given in the first condition the point 1, 3. So condition 2, the limit statement, we have to have graphically a hole there at the point 1, 2. 2 being the limit value for condition 3. Okay, now this is what our graph looks like considering our tip. For each of those given conditions, we just basically sketch a small portion of the graph that's relevant to those important x values. Now, how we complete the problem is basically just connect all the pieces together. Now, there's not a ton of variety. All your basic graphs that you might have drawn have these similar features, provided it's correct from these limit statements. But there's technically an infinite number of correct answers here for you to draw. As we continue later in the course, when we have more ideas, we'll be able to have more information that will allow us to draw a more accurate graph. But right now, with these small pieces of the graph drawn around each important x value, we just connect them together, and here is one possible graph. And that's it. So again, keep in mind there's many possible graphs, but they all have these same basic features looking something like that. And we just connect the pieces together. Again, this is going to put us on our long-term goal of curve or graph sketching. What we're seeing here is that concepts with calculus, limits, do tell us something about the graph. As we continue in the course, when we introduce derivatives, whatever that is, we'll use those ideas to help us sketch a graph.